The formal definition of what it means to be continuous is right here. And again, it kind of makes sense once you get through all the litigation. A, B, and C all must be true for the function to be continuous at x equals c. Let's see what that means. I'm going to make a picture. And I'll put a random place called C. Doesn't really matter where this is. I'll make the function come along, just doing its thing. When it gets to C, it has to exist at C. If there's a hole, obviously that's not going to work. We'd have discontinuity. We have to fill that hole in. Same thing you can't have in the asymptotes. All right, well, you have to still say B and C because there are other things that can happen. For example, for C, what if I took this out and I put it up here, just like a space above? And then I could get all legalistic. I could be like, ha ha ha, you just said f of C must exist. It exists, it's up here, so I've covered, requirement A, but I still have discontinuity. And so what C says is, no, look, as you approach C from the left or the right, it has to be equal to what you actually see when you're there. So this statement C says, hey, little green dot, get back to where you belong. Get back in that, thing, patch that hole up. All right. And then the other thing, B, is just another piece of litigation in the middle. That's just saying, hey, the limit has to exist. Because technically, you could do this. But yet you still have your f of C, and you have a limit from one side. So this just sort of cleans up the language to make sure that, you don't have some sort of jump discontinuity. It forces the function to come together. I'm not going to make you memorize this slide. I just wanted to show you the complex language behind what we're doing. As long as you can find limits, like we did on the previous slides, you're in good shape. All right, we're going to pick up where we left off on section 1.4. This time we're going to talk more about continuity. And you may remember from the past, there are three types of discontinuity: point, jump, and infinite. And we have to tell which type it is. Again, there's a quick visual reminder of what they are. Well, first off, when you look at number 14, there's an x minus 2 in the denominator. Since dividing by 0 is problematic, we know that there must be discontinuity at x equals 2. We just have to determine what type. Now, since we can't factor the numerator, after all, it is just a 3, there's no way to cancel another x minus 2, numerator and denominator. The x minus 2 in the denominator is just there. We're stuck with it. And so that's going to make this infinite discontinuity. This will turn into a vertical asymptote there. Okay, number 15, we can factor a 2 out of the denominator, leaving us with x plus 3. I think it's pretty obvious that there's going to be some type of discontinuity at x equals negative 3. We'll have to see what type it is. The numerator also factors. Imagine that. I'm making these problems up, so this will happen. And not too surprisingly, it's going to be another x plus 3 up there, coupled with an x minus 6. The x plus 3's will cancel away, giving us simply y equals x minus 6 over 2. Now that would look like a line, but again, the original problem was black, not green, and so there will still be discontinuity at x equals negative 3, even though it canceled away. But this time, because of the canceling, it's not infinite discontinuity. This will not be a vertical asymptote. It's simply point discontinuity. Okay, number 16, we have y equals the greatest integer function with an x inside. We already know what this looks like. It looks like a series of stair steps. So here we can say that there is obviously jump discontinuity. And where does it occur? At each integer. And we want to say integer, not whole number, because the whole numbers don't include the negatives, so we want to include them as well. And of course, you may remember that the abbreviation for integers is the fancy Z with the double slash diagonal. So you can use that if you'd like as well. All right, 17. Let's factor. Denominator first, I will take out an x, leaving me with x minus 4. Numerator, that's going to break down into two binomials, x minus 5, x minus 4, with the x minus 4s canceling away. All right, there are two different points of discontinuity. One was at x equals 4. The other is x equals 0 right here. Now, some people are thinking x equals 5. No, not necessarily at all, because this x minus 5 is in the numerator. We don't have to worry about plugging a 5 in and dividing by 0. In fact, if you plug a 5 in, it won't be any sort of discontinuity. It'll simply be an x-intercept. So that's okay. The denominator is where we're focusing our attention at. So there's going to be discontinuity at 0 and at 4. Because the x minus 4s canceled away, that's simply point discontinuity there. However, this x did not cancel, so therefore it's infinite discontinuity at x equals 0. That will be a vertical asymptote. All right, on number 18, we have some absolute value. It seems like your teacher is trying a little bit too hard to make some more jump discontinuity. Hey, I've got to do what I've got to do, right? First question is, can you legally factor this 2 out and just make it x plus 4? That seems to be desirable because there's an x plus 4 in the denominator, but is that a legit step, or am I just making that up? And the answer is, yeah, that's okay. That's okay to do. Because this is an absolute value up top, if it was already positive, if the 2x plus 8 was something positive and I factor out a 2, it would still be positive inside, no harm. But if the 2x plus 8 was going to turn negative and I factored out a 2, the x plus 4 that's left over would still become negative inside. So yeah, factoring out a 2 is not going to hurt here. Okay, that's totally okay to do. What's not okay is to cancel. If that red step was legal, then absolute value in parentheses would be the same thing. And clearly in math, they're not the same thing, so don't do that. Instead, whenever you're faced with something like this, you always want to make a quick graph of it. And since we know that there's some sort of discontinuity at x equals negative 4, I sort of focus my attention along that dotted line. That dotted line is not meant to represent a vertical asymptote. That's just for me to focus on. It's sort of like training wheels for me. All right, I'm going to pick a number larger than negative 4 and try it into my work. Let's try, I don't know, positive 1. I'll throw positive 1 in. If x was 1, I would have this. I would have 2 times the absolute value of 5, which of course is just a 5. Speaking of just a 5, that's what the denominator is. Those would cancel away, and you'd just be left with 2. So it goes through the point 1, 2, which is right here. Of course, if you tried other numbers like 0, or 10, or anything else, or even 100, you can see that the canceling is always going to happen. The pair of 104s are going to cancel away, and so you'll always be left with just this 2 right here. So this is going to be a pretty boring graph. It's just going to stay 2 the whole time until you actually hit negative 4. We cannot plug a negative 4 in because we simply can't divide by 0, so that has to be an open circle. Now let's pick something less than negative 4. How about negative 9? Just randomly. All right, that's going to end up becoming this. We have our 2. We have an absolute value of negative 5. And down below, it's just negative 5. Again, those will always match, except this time, the absolute value turns positive, but the denominator does not. Now those 5s will always cancel because they're always going to be the same number. But instead of just having a 2, now you're always going to have a 2 over -1, which is -2. And so you're going to be down here at -2 for all these numbers. So what's happened is we have produced jump discontinuity at x equals -4. Number 19 is a piecewise function. Again, we have to find the x values where the discontinuity occurs. And an obvious candidate for that is x equals 4 because that's where the rule changes. If a function is likely to break or snap somewhere, the place where the rule changes would be an obvious suspect that we should probably check out. So let's try a 4 in just to see what happens. If you put the 4 here, you're going to end up with 20 minus 8, which is 12, over the 4 there. Okay, that's going to make 3. If you plug the 4 in here, now I realize there's no equal to underneath. It's simply x is greater than 4. But we're plugging a 4 in anyway because we're basically working with a limit. That's going to be 16 minus 13. That's also 3. So since they both head towards 3, they're going to connect at the point 4, 3. They're going to come together. And so therefore, it's continuous there, even though the rule changed. Now, obviously, if these 3s right here did not match, let's say one was a 3 and one was an 8, then you would have jump discontinuity there because you'd have a 5-unit gap. Okay, but that didn't happen. It's continuous there. However, there still is discontinuity in this graph. Do you see where? X is not allowed to be 0. You would be dividing by 0 right there. And since there's no way to cancel that with anything in the numerator, at least not legally, it's just going to be stuck there. And so we will have a vertical asymptote at x equals 0. So that is infinite discontinuity. The other thing is the directions have changed. It says, instead of what type of discontinuity, point, jump, or infinite, and in this case it's infinite, they say state whether the discontinuity is removable or not. Removable discontinuity is just another term for point discontinuity. The reason we call point discontinuity removable is if you have a point discontinuity, it'd be something like that, you can easily remove it just by saying, okay, there's the equation, and if x is, let's say this is happening at 0, then y is whatever, 8, or I'm making up a number, you can fill it in. And therefore you remove the issue. You can't really remove the issue if you've got some major, jump discontinuity or infinite. You can't fix that just by saying, make y this number, plug the hole, patch the pothole along the road. Not easy to do when you've got more of a cliff. Or worse yet, a vertical asymptote. So basically, long story short, if this ends up being point discontinuity, we say removable. If it's jump discontinuity or infinite discontinuity, it's non-removable. Since this is going to be a vertical asymptote, we have non-removable discontinuity at x equals 0. Interestingly enough, I could change the answer completely if I flipped around the inequality symbols. Let's say that I had x is greater than or equal to 4, and this was x is less than 4 below it. Now the function would be continuous, and there'd be no discontinuity at all because you're like, dividing by 0. And I'd say, hey, not to worry. That rule is only good if x is greater than or equal to 4, so you wouldn't be plugging a 0 in anyway, so you're safe. And so therefore this discontinuity at x equals 0 wouldn't exist. Okay, so I can play that game as well. So you can't just assume it's jump discontinuity, non-removable, just because you see the bracket and you see the piecewise look. You still have to investigate. Our textbook will occasionally ask you to find the value of k that will make the function continuous. Here's the k right here. I'm going to put it in blue. Because in my world, k's and x's start to look alike with the way I write. Okay, in this piecewise function, the top equation, or the top part, is going to be linear, and the bottom is going to be some sort of a quadratic, parabola, because I see the 2x squared. We're hoping that they come together at x equals 6. In fact, we need them to come together there because we need the function to be continuous. So what I'm going to do is, obviously the x equals 6 is what we're worried about. So we're going to turn all the x's into 6's and just see what we have. All right, starting up top, 5 times 6, that's 30 minus 3, that's 27 fourths. And I need to make that equal to the other part. Again, I still have the 3k minus 2 in the denominator because I don't know what k is. If I knew what k was, I wouldn't be doing this problem. Plugging the x equals 6, I realize there's no equal to, but I'm doing it anyway. Plugging the x equals 6 in, we'll get square, that's 36 times 2, that's going to be 72 plus 9, that's 81. All right, so now I can just cross multiply to solve. Now, if I don't want to cross multiply, I can get real savvy because I realize that I have a 27 and an 81 in the numerator. And I realize that 81 is 3 times larger. It's like a times 3. So if I want, I can do the same thing down here, and I can be like, you know what? This needs to be a 12. So 3k minus 2 is simply 12. And basically, I've avoided the big numbers that I would have gotten had I cross-multiplied. You get the same answer either way. Add 2 to both sides, and divide by 3, and you have k equals 14 thirds. And that is the correct answer. So what we're saying here is if k is 14 thirds, the two sides here, the two parts of this piecewise function, left and right, are going to come together perfectly at x equals 6. If k is any other number in the world, you're going to have some discontinuity, most likely jump discontinuity there at 6. So 14 thirds. Which happens to be the correct answer.